And it's sort of interesting. So let me leave that up for here. So the first point, sort of everything I've done so far basically says, if I have a matrix A, it's a transformation, I really want to know what A to the m is, first point. Second, if the eigenvalues are distinct, I can diagonalize A. Once I diagonalize it using the similarity transformation, I have a very nice way of computing A to the m. Okay, that's all we've gotten to do so far. Now I want to kind of show a couple of properties about eigenvalues and eigenvectors which make life a bit easier. Okay, so the first one is that if A is square and diagonal, then the eigenvalues are the diagonal elements. And we saw this already last time, so I'm just going to state this. And this comes simply from the expansion of A in terms of the determinant. You know, when you solve the characteristic equation, it's going to look like basically lambda minus AII is going to be, so you're going to have essentially terms of the form lambda minus AII, okay, equals 0. That's going to be the characteristic equation, so you can read it off directly. So that's why we like diagonal matrices. And diagonalization essentially converts any matrix A with distinct eigenvalues into this diagonal matrix. Okay, that's the first fact. The second thing is if A is square and symmetric, okay, if it's symmetric, I'll explain what that is in just a minute, then its eigenvalues are real. And symmetric just means that any element Aij equals Aji. So we cannot have a matrix where we have the diagonal elements and everything here is symmetric across the diagonal. So Aij and Aji are the same. And if it's symmetric, then you can show that all the eigenvalues are going to be real. Okay, so that's a good thing to have. All right, and of course the diagonal elements will need to be real as well, right? If the diagonal elements are complex and it's symmetric, then well, if it's zero, if it's all zeros and symmetric, well, you know, we know the diagonal elements are the eigenvalues, so diagonal elements are real. Okay, then this other thing is called the I don't know how to pronounce this. I'll write it down. Maybe one of you can tell me what the right Gerachgorin. How do you pronounce this? Gershgorin. Hershon. I thought it was Hershon. Does anybody have any idea? No? Okay, we'll just call it the G circle theorem. It's a circular sort of and what it says is like this. Let's take any matrix, okay, and let's say the elements are complex. Then what we do is that we take the diagonal elements, which are going to be AII, okay, and we look at the magnitudes of the other elements over here. So this is A11 actually. This is A12 all the way to A1n. So let's just look at that. So for a complex number which is written on the form, let's say x plus iy, okay, the magnitude is given by written as x plus iy, okay, equals square root of x squared plus y squared. And the geometric interpretation is that x plus iy is somewhere over here. This is x, this is y, this is x plus iy. And you know, this is sort of a circle, and this distance from the center of the circle, the origin, is the magnitude. It's x squared plus y squared. So we take the sum of the magnitudes of A1j, so j equals 2 to n, okay, and we take the magnitudes of these elements over here. Let's call that some value r. Then we can say that the eigenvalue, okay, the eigenvalues for this lie in a circle on the complex plane, lie in a circle of the complex plane centered at A11 and with radius r. Okay, somewhere there is where the eigenvalues are going to lie. And the same thing is true for each of the other diagonal elements, A22, A23, and so on until Ann. Okay, so we can take each of these diagonal elements and view them as centers of disks, okay, or circles in the complex plane. And okay, we're going to have sort of these things over here, and the eigenvalues are going to lie somewhere inside those disks. Okay, that's the so-called circle theorem. And intuitively, what's going on is this. Let's say that it's a diagonal matrix. If it's a diagonal matrix, we know that all the off diagonal elements are 0, right? All the off diagonal elements are 0. So we kind of have this degenerate case of a disk, which is just a point over here. And so the eigenvalue obviously lies right here at this point. Okay. As we add more non-diagonal elements, as we expand it, what happens is that the space in which the elements could, the eigenvalues could lie, as it grows a little bit larger, possibility grows larger. Okay, so to the extent that we, if I show you a matrix, okay, we show you a matrix where the largest values lie on the diagonal and the off-diagonal elements are small, then I can pretty much tell you where the eigenvalues are going to lie. Okay, I can have a pretty good idea where they're going to be. Okay, and that's good, because if I have a large matrix, if I have some set of transformations which is going to push all the values towards the center, and if I can invert that transformation, okay, like the similarity transformation was taking this, okay, was making it diagonal, okay. But suppose there's some other transformation which I don't know. Let's call this. I don't want to tell you what it is just for a moment, where it's not diagonal, but it's sort of diagonalish. All the mass is considered diagonal, and it's invertible transformation. So I take the transformation x. Okay, so I'm going to do, let's say, d prime is going to be some y times a. Okay, so y inverse a y. Then I can go over here. Right, and so when I look at this d prime to the power n, I kind of know what to do, because it looks diagonalish. I kind of know I can sort of ignore the off diagonal elements, for example. And so this is the intuition behind the Jordan canonical form, because remember, to do this, A must have distinct eigenvalues. But suppose it doesn't have distinct eigenvalues, then what we can show is that there does exist a transformation like this, which is invertible, which takes A and converts it into a form where almost everything is on the diagonal, plus we have some elements which are one above the diagonal, okay, and that's all. So you have matrix which looks like this. We have all these things over here, and then we have some elements just above the diagonal, okay, and that's called the Jordan canonical form. And the Jordan canonical form is not as nice as the diagonal form, because we can't just read off the eigenvalues. But this theorem, the circle theorem, tells us that, yeah, it's good. We can sort of, to first approximation, treat these as being the eigenvalues, even though they aren't. Okay, so we can kind of read off. Again, this is very hand-wavy, and I'm not going to go more into this. But for those of you who are going to be going further down linear algebra, this is where you'll see a lot of Jordan canonical form, what I call the Jordan blocks, and the effect of Jordan blocks on how we compute a to the m. Okay, this is giving you a sense of that. So let me do an example just to just to set this. So let's consider the matrix. Okay, where did I put it now? I'm shuffling the order around as I teach it, so that makes it a bit right. Here we go. So let's take this matrix over here, 9.1, 0.8, 0.3, 0.8, 5.8, 0.2, 0.2, sorry, 0.3, 0.2, 6.5. So the two things that are going to should strike you right away. One of them is that if I consider the main diagonal, the weight, the magnitudes are mostly in here, 9, 5.8, 6.5, and all the off-diagonal elements don't have that much weight. The magnitudes are not that large. Okay, that's the first thing. Second, it's square symmetric, okay, because we have this relationship over here, 0.3 to 0.3, 0.2 to 0.2. So we know it's symmetric. So if it's square, it's square symmetric, the eigenvalues are real. So we know it has real eigenvalues. And second, we know that the eigenvalues are going to be on these disks with these centers, and of radius what? It's going to be 1.1. This one adds up to a disk of 1.0. This is going to be a disk of 0.5. Okay, so the diagonal values happen to be reals. So in the complex plane, which is this is I and this is going to be the real plane, they actually are on the real axis. So we have 9.1, 5.8, and 6.5. Okay, something like that. And we know that the disk is going to be like this, right? So it's 9.1 of radius 1.1, so it's going to be 8, so something like that. But it can't be in the complex plane. It's got to be in the real plane. So we know that it lies in this interval from here to here. Okay, similarly, it will be a circle of size 1 around 5.8, so it goes from 6.8 to 4.8. So it's in this interval, and this interval over here is going to overlap. So we basically get a bunch of intervals, and we know just from looking at it that all the eigenvalues are going to be real values somewhere in this interval, or in this set of intervals. It turns out to be 2 intervals, okay? And that's really nice, okay? Because computing eigenvalues can be complicated. For this, to solve this, I have to solve the cubic equation, right? I got to solve the cubic equation, but here I don't need to. I can simply kind of tell you this where the eigenvalues are going to lie. However, I still haven't told you what the eigenvectors are, so I can't do this similarity transformation, so on and so forth. But it's kind of nice. I can show you a matrix and say, where do they lie? Here they are. You know, it's a kind of a good party trick. So you know, if you go to a grad student party, you can say, I can tell you the eigenvalues where they lie of this matrix, where they approximately lie. Who knows? Somebody might buy you a beer, you know, for this. It's a math party trick. Okay. So any questions about this? Okay, I want to take a moment to talk about something else, and then we'll look at actually computing eigenvalues for real instead of just talking about it. The next thing I want to talk about, which is related to this, is called the principal eigenvalue or dominant eigenvalue. And again, to introduce this, let me just use this simple example. Let's say that I have some vector v, which I'm writing in terms of the eigenvalues. Let's say I equals 1 to m, ci xi. So what I'm saying is that the eigenvalues, in this case I'm using x to be the eigenvalues. The eigenvalue spans some eigenspace. V is a vector in the eigenspace with the linear combination ci's given over here. So that's pretty straightforward. You know, the eigenvalues form a linearly independent set, so the basis vector, so they form a basis, and from this basis I have this. Okay, great. So what we're going to do, and so we had some, and of course there's some underlying matrix A that's what's associated with this. Then we can say that A to the n applied to V is equal to A to the n applied. It's applied to this thing over here, sigma I equals 1 to m ci xi bar, and by the fact that ax is lambda x for these eigenvectors, we get the equation that it's going to be sigma I equals 1 to m ci lambda I to the n xi. Okay. So this is what we saw earlier for the case of 2. I just generalized it. But what's interesting here, once you look at it, is that we have the following thing. We have a sum which has only one term that sort of depends on the value of n over here, which is lambda I to the n. Okay? So when we take a bunch of numbers, okay, and we're going to just take the nth power of them, what happens is that, let's just look at this. I'm just going to take lambda, and here I'm going to plot lambda to the n. Basically, it starts at 0 and goes up pretty fast. Okay? So if I'm taking the sum of these n values, ignoring the xi and ci and so on, if I take a sum of these values, I have some value here. Let's say I have lambda this, this, this. These are the 4 values of lambda. These are the 4 magnitudes of the eigenvalues, right? Let's look at the sum. So I have some contribution from here, which is way up there, and that's something, this is, let's just ignore this. There's something from here, and there's something from here. So I got this value, and one all the way up at the ceiling, okay? I don't really care what these values are. Those are all in the rounding error, basically. All I care about is this value over here. I can just pretend these don't exist. They just don't matter, okay? So again, this is the eigenvalue trick, okay? I'm giving a bunch of eigenvalues, okay? The largest one by magnitude is the only one that really matters. Okay, when n is large, when n is small, okay, it doesn't matter. If lambda square, maybe you care about, let's say n equals 10 even, okay. This value of is going to be so large, we don't really care about the rest. So remember from the circle theorem, I kind of know where the eigenvalues are going to lie. And so I can guesstimate where the largest eigenvalue is going to be. Now I can tell you that the behavior of a to the n on any vector v, which can be expressed as this, is dominated by the effect of the principal eigenvalue. Dominant means there's more than one and it has the same value. Remember, once we saw the eigenvalues plus minus I, so they're both equally large. Okay, we're kind of out of luck. But if one is much larger than the others, it's called the principal eigenvalue. This is what it looks like, okay? And so this gives us now some intuition of what to look at. If we find a matrix where it looks something like this, okay, and we have mostly the mass is concentrated along the diagonals or values, and then this one is the largest value, okay, and all the others are somewhat smaller, then the behavior of this transformation is pretty much dominated by that one large value, okay, because this plus its off diagonal elements is going to be more or less this, okay, and I can kind of guess that the effect of this matrix is going to be dominated by this largest diagonal element, okay. So again, it's intuitive. I'm kind of giving you a sense of things, and all this can be formalized and so on, but you want to understand. So just looking at a matrix, you can say, oh yeah, that element there, that's what's going to dominate everything. Why? Because of the principal eigenvalue. And there's an example over here which you can go through where I computed the, I believe, the 11th power or something like that, or 10th power, and it turns out that this, the dominant eigenvalues, really so much bigger, you don't really care about the other eigenvalues at all. Okay. Any questions about this so far? Okay, so after the break, I'll talk about how to compute eigenvalues, but I want to kind of give you the reason why the principal eigenvalue is so important. When we study graph theory, and we want in this class, it turns out that a graph can be represented by a matrix, the adjacency matrix, and certain graph properties are related to eigenvalues, okay, especially connectivity is related to eigenvalues. And we can say a lot about the graph by looking at its connectivity matrix, and the eigenvalue is the connectivity matrix. And in Friday's lecture, we'll see how Google uses this idea to compute PageRank. So it turns out PageRank computation is actually nothing more than eigenvalue computation. Actually computing the dominant eigenvalue is what you want to do. And we'll see how Google does that. At least the early Google algorithm is based on this. So we'll talk about that next time. But today I'll talk about just computing the eigenvalues, dominant eigenvalues. Okay, that was the principal eigenvalue. Let's kind of go on to finding eigenvalues. Oh, and I guess there was a question about what is the circle disk? So I'll just solve that. So the matrix we had was the eigenvalues are 1 minus 2 by 3, 1, 2 by 3. Eigenvectors for the matrix 1, 9, 4, 1. We knew this from before. X is from here. I just left it on. So that's the matrix X is this. So the diagonalization of A is going to be basically X inverse AX, where X is this. So if you just wrote that, that's the answer. You don't really need to sit there and compute the inverse, but you felt like doing it. It's good for you. It builds character, so you perfectly, you should have done it. But this is all you really need, okay, for the solution to the thing. And then the other one was what are the disks corresponding to the matrix 1, 9, 4, 1. And now we can see it's just going to be 1 plus I0, if you want to be really precise, is the center, and the radius is going to be 9. Okay, and the other one is 1 plus I0, and the radius is going to be 4. And if you want to draw it, it's going to be on the x-axis 1. We have basically of radius 4, and then another disk which is of radius 9. Those are the two disks, and eigenvalues are going to lie somewhere there. If you remember, the eigenvalues of this are minus 5 and 7, and you'll find that minus 5 and 7 both actually lie inside one of the disks. The question?
What was the task in the second exercise?
To write down the diagonalization of this matrix 1, 9, 4, 1.
And the answer is just x minus 1?
X inverse AX, where X is this. If you want to, you can go compute it.
Okay, and
what's the actual answer? I don't know. I didn't do it. Does anybody have the answer? 700 minus 1?
Minus 5.
Minus 5. Okay, sure. Those are actually also, oh yes, so maybe I should, this pattern is kind of confusing. This, of course, is the eigenvalues. Okay, yes,
Is that 1 plus I0, that I0 part is important?
No, it's not. Yeah, if you want to be really particular, because the circle theorem is for the complex, then we treat this, but no, this is not necessary. If you just say 1, 9, that's okay, right? Because in the real plane, we don't have circles. We just have intervals, right? Okay.
So the answer is minus 3 to 5 and minus 8 to 10, huh?
Yeah, that's right. You can do that as well. Yeah, this is minus 3 to 5, minus 8 to 10. Yeah, you can do that as well. If you write it either way.
One of them is minus 8 to 10.
Yeah, the union, not the union is yeah, minus 8 to 10. That's equally acceptable. It's just the way you represent it, but you just need to understand where the disks are. Yeah. Okay. Yeah.
But it's not symmetric.
No, but if it's not symmetric. It's being symmetric is sufficient, but not necessary in this case, right? Just because it's symmetric, if it's symmetric, it will be real. But if it's not symmetric, it may still be real. Right, it's sufficient but not necessary. Okay, let me keep moving on, because I've actually managed to spend more time on this than I wanted. Okay, so how do we find eigenvalues? We can't find all eigenvalues right away, but there are some tricks for computing the dominant eigenvalue. And the most common trick is what's called the power method of computing the eigenvalue. So to approximately compute the dominant eigenvalue of, okay, the method is called the power method for a very simple reason, because we take the powers of A. So what we do is we take the matrix A, which is we want to compute the dominant value of A, and we just take any arbitrary initial vector x0. Arbitrary, just pick anything you want, apply A to it, okay? And then you compute what's called the Rayleigh ratio. And the Rayleigh ratio is given by, let me just write this down, xk t a xk. I'm leaving out the bars over xkt. Okay, so, and if we compute the Rayleigh ratio, then this is going to, and this is the same as, because, okay, and we'll just say x1 equals ax0, so it's nothing more than xt x k plus 1 over xt x k, like, of course, where t means transpose. This ratio is going to converge to the dominant eigenvalue. Okay, that's the kind of the trick. Why does it work this way? It really comes down to the fact that the transformation is taking some arbitrary vector, initial vector, and scaling it up. Right? It's scaling it up by the values lambda 1 and lambda 2, so two eigenvalues in 2 dimensions. So let me just write that down. So ax0 is going to be nothing more than c1 lambda 1 x, sorry, v0 plus c2 lambda 2 v1, okay, lambda 2 v2. If the eigenvectors of A are v1 and v2, then applying A to x0, where if the and x0 can be written as c1 v1 plus c2 v2, then A x0 is nothing more than this, right? And A to the m x0 is going to just take these guys and make them to the m, right? We're just going to scale it up. The only thing that matters is this one over here, right? So if you take the ratios of these products xtx, it turns out that that particular thing is going to be scaled mostly by the dominant eigenvalue. So xtx is going to be inflated by this value lambda. So it's going to be pumped up by lambda each time, which is the dominant eigenvalue, and we can ignore the other one. Okay. So let's do the homework example to just kind of give you a sense of what's going on. So here I start with the initial value 1, 1. So if you don't have 1, 1, your answers are going to look a little bit different. But this is A, it's 1, 9, 4, 1. And I just start with 1, 1. And that gives me the vector 10, 5. So this is x0, this is x1. So we just need these two values, xkt, xk plus 1, xk transpose xk. So so we're basically looking at 10, 5 multiplied by 1, 1 over, or actually the other way around. So 1, 1 multiplied by 10, 5 over 1, 1, 1, 1. Okay? And this is 15 over 2 is 7.5. Okay, this is pretty good because remember the dominant eigenvalue for this was 7, right? 5 is the smaller one. The main one is 7, and with just one simple computation, I just got to 7.5 right away. And if you do it one more time, you should be getting to 6.6 bar. Okay, and yeah, in the interest of time, I'm not going to do it, but it's basically taking 10, 5 and doing it. Well, maybe I'll just show you what happens in the next step. It's really pretty easy to do it. In the next step, you're saying 1, 9, 4, 1 applied to 10, 5 is going to be 55, 45. And then this ratio is going to be given by 100 over 15, which is 6.6. So we're kind of going above and then a little bit below. And if you do it 3 or 4 times, you'll get to 7 pretty quickly. And that's quite nice, you know, and it's showing you how the dominant eigenvalue can be extracted using just this Rayleigh ratio. Okay. So any questions about this? So hopefully most of you got this. Yeah.
Can we extend 2, 1 instead of 10, 5?
2, 1, yeah, sure, you can do that. Yeah, that's fine. I mean, that's normalization. I'll talk about normalization in just a minute. Yeah.
How many, like, if you have this kind of exercise, how many steps do you need to do?
If you do 2 steps at least, if you do more than 2, that's good. But I just did 2 for my solution. Okay, this gives you the dominant eigenvalue. How about the dominant eigenvector? it turns out that we can do that. We can compute the dominant eigenvector as well. And to compute the approximately dominant eigenvector, we need another fact. And that fact is that, again, we use the power method. What we do is that we have to renormalize the eigenvector. So what we do is we rescale or need renormalize. It's another two words that people use it. The value of the vector xi, so that maximum element is 1. Okay, if you do this, then xk is the dominant eigenvector. Okay, and that's the dominant vector corresponding to the dominant eigenvalue. So what we're looking for is the vector 1, 2 over 3. Okay, and so let's just. I guess I didn't really ask for that in the homework, but I'll do an example showing that. So let's say we have the matrix 4, 6, 12, 4. Okay, and we're going to have the okay, and so we're going to use the okay. So okay, I'm going to go back to the example 22. Okay, then let me start with the initial value 1, 1, and then x1 is going to be just the sum, so it's going to be 10, 16. Okay, so I need to renormalize this, right? Which means I've got to make this look like 1, so which is the same as, or which is, I change it to 0.6251. Okay, so that's the renormalization step. Okay, and then using this, we get x2 using this one over here is going to be 4, 6, 12, 4 multiplied by 0.6251, and that gives us the vector 8.5, 11.5. Okay, and 8.5, 11.5, we're going to renormalize this again. And we get over there the vector 0.6961. Okay, this is going to be x2 after renormalization. Okay, so you can see what happens is I'm going to take this value here, plug it in, multiply by the matrix A, and keep doing this. And what happens is that eventually we'll get, after a few steps, we get this to be 0.707 and 1, and which is pretty close to the eigenvalue over here, which is root 2, 1. Okay, so we can see that the dominant eigenvector is being extracted pretty closely by using this trick over here. So that is the technique for extracting dominant eigenvalues and dominant eigenvectors. Again, this is only giving you the one value, okay? But in many practical situations, that's the one you really care about. Okay, using dominant eigenvalue, we can roughly guess what the effect of the transformation is on any matrix over here. Okay, one thing you can do as an exercise just to see that you're understanding things is that for the matrix 1941, which has this matrix which has these eigenvalues, eigenvectors, can you get to this eigenvector? How many iterations does it take for you to get to the eigenvector? Basically, it will be 1.66. Okay, how many iterations can you get there? I suspect that in 3-4 iterations, you should probably get fairly close to that. It's kind of just worthwhile trying that out to see how that works. Okay, any questions about this so far? So I'm going to summarize all this by just giving you a little bit more intuition. So we started out with understanding eigenvalues as just being sort of the solution to some equation. Okay, so a matrix is a transformation, and the eigenvalue is a solution to something which tells us that this matrix looks like the multiplication by a constant factor. Okay, that's all we really said. But now we're getting some hidden depths, okay? And the hidden depths is saying that the transformation can be approximated. Okay, we have transformation on, let's say, a 25-dimensional object. It's going to do something. It's going to actually take the initial vector and scale it and rotate it. Okay, that's what it's going to do. And it's going to do it in some crazy way. However, we can just figure out roughly what it's doing by looking at the dominant eigenvalue. Okay, by looking at the, because of the fact that the multiplication, repeated multiplication, exaggerates the dominant eigenvalue. Okay, so to the extent that we can compute the dominant eigenvalue by inspection, because if it's diagonal, or if it's sort of diagonal by looking at the circle theorem and saying this is where the things, where the eigenvalues lie. So you know the largest eigenvalue is going to be somewhere in this range. You know, if you can ballpark it, we get a ballpark idea of where things are going. Okay, and using the Rayleigh ratio and this normalization, we can quickly iterate to figure out what the values are, what the values of the dominant eigenvalues are. By the way, this Rayleigh ratio is also a trick for you to compute square root of 2. Okay, you can compute the value of square root 2 using Rayleigh ratio quite nicely, and this is another sort of mathematical trick. If you can choose the right matrices, then this ratio is going. If we know, you know what square root 2 is, we can actually find it using this matrix 4, 6, 12, 4. And you know, so it looks like magic trick. I give you this matrix, I say do these things, and the values of square root 2 keep popping out, okay, from there, which is kind of a nice thing to have. Okay. So that's roughly the intuition. The next class, we're going to go into stochastic matrices, which arise in queuing theory, which we won't go into, but they also arise, as I said, in graphs of various sorts. So this notion of dominant eigenvalue becomes really the basis for web search, which we'll see. Okay, stop here.